Good morning, good afternoon, good evening, depending on where you are. Let me try to give you in this short lecture an overview of what approaches in principle exist for measurement uncertainty evaluation. So the main question of uncertainty evaluation in a typical analytical lab is the following. People typically know more or less what are the sources of uncertainty in their measurements. Yeah? And they also have different data available, such as control charts, proficiency testing results, results of replicate measurements, results of certified reference materials, etc. And the typical question is this one: how to use these data to take these uncertainty sources into account? And the different approaches for uncertainty evaluation offer different solutions to this question. And to quite some extent, what I will be explaining is based on this scheme, which in turn comes from a Eurolab report, which actually is quite old already, but it's still fully valid and actually gives a nice general overview of how in principle measurement uncertainty could be evaluated. So let me briefly explain here. First of all, everything starts with definition of the measurand. And in addition to that, of course, also knowing the uncertainty sources and also the measurement method. And now, depending on how it is done, the approaches can be either single laboratory or interlaboratory approaches. By single laboratory, we mean here that you use data from your activities in your laboratory, from your measurements that you've done. By interlaboratory, we mean that essentially interlaboratory comparison measurement data are used, which oftentimes may mean that no data from your lab are taken into account at all. Yeah? And now these single laboratory approaches can also be broken down in two, depending on whether it's model-based or not. Model you, of course, always need for calculating your measurement result. But not always is model actually necessary for evaluating uncertainty. And so if model is necessary and if the uncertainty evaluation goes on the basis of the model, then we speak about the so-called modeling approach, oftentimes also called component by component bottom-up approach, also the traditional or classical ISO-GAM approach. Yeah. And secondly, if model is not directly used for uncertainty evaluation, then we can speak of in-house validation data-based or within laboratory reproducibility and bias-based, sometimes also called top-down approach. And there are actually many different ways how this can be done. There are different formalizations, and very importantly for today's event, this approach is what the new Eurachem guide will explain and detail and contain. So in some sense, this approach is the most important for us today. And now, about these interlaboratory approaches, I will come back to them later, but I will then later on explain that these are, I would say, of limited use. They can be used only in the case of very, very standardized methods, so that we don't really spend much time on them today, because in many, if not most laboratories, I would not really maybe recommend using them. But now, before going to the approaches, it's also quite useful to look at briefly, let's say, a division between different effects that affect your measurement result. And it is useful, it turns out, to distinguish between short-term and long-term approach, or we can view things in the short-term or long-term way. Let's start with the short-term. Here, all the effects that affect measurement result, meaning all the sources of a measurement uncertainty, can be broken down into random effects within day, which is oftentimes called or characterized by a repeatability, and all other effects which all within a day work as systematic effects or cause bias. You know? But now, If we look at the same thing in the long term, then all the random effects we could characterize by the so-called intermediate precision, or within lab reproducibility, as it is also sometimes called. And the systematic effects that remain would be called something like long-term bias or lab and method bias. And if you notice, then this block is much shorter here than this one, which means that over a long time period, lot of things that cause bias within a day, meaning have systematic effect within day, in the longer term will act as random effects. A very easy example is a titrant concentration. If you occasionally re-standardize your titrant, then on every single day, the titrant concentration's difference from the, let's say, absolutely true concentration is a systematic effect. But in the long term, sometimes you got this titrant concentration maybe slightly lower, sometimes slightly higher, sometimes slightly lower, sometimes slightly higher, meaning in the long term, it becomes a random effect. And it turns out, if we go to the next slides, it turns out that making this distinction is quite useful. And also it turns out that different approaches approach the effects differently. And I will explain that in a minute. What we should remember from this slide is that the longer the time frame that you take, the more effects change their status from being systematic to being random. Now, let us start with the modeling. So the uncertainty evaluation using the modeling approach typically works as follows. People build measurement model where the output quantity or measurement result is here, all kinds of input quantities, which are concentrations of solutions, peak areas of standard solutions, peak area of the sample solution, etc., all those different things that are measured are input quantities. And then the combined standard uncertainty of the result can be calculated via this formula, which is presented in many different documents and which looks very, let's say, difficult, but actually is not so very difficult. What is important here is that for every input quantity, there's something called uncertainty component, which needs to be quantified. Yeah. And in every uncertainty component, this partial derivative here is something called sensitivity coefficient, which tells us how sensitive is the result to this particular input quantity. I have actually presented here this equation in a simplified way so that the possible correlation is ignored. In any case, this modeling approach is quite mathematical, so quite some mathematics is needed for using it. Now, what are the important aspects here are the following. First of all, you need to estimate uncertainties of input quantities, and your model must be built in such a way that all the uncertainty sources, or actually to be exact, all the important uncertainty sources are in some way represented by uncertainties of input quantities. Yeah. So that if there's some effect that does not influence any of the input quantity in the model, but has effect on the measurement result, then the model actually is not okay for this particular case, which is a tricky thing. It's not always so easy to build the model in such a way that it really takes everything into account as needed. Secondly, in this approach, you can put in data of the particular measurement that you did on a particular day. Meaning you can really get the uncertainty of that particular result. Because all such things as all specifically the peak areas, repeatabilities, etc., all that you had on that day go into that calculation. Yeah? We will see later on that this is not the case with the remaining approaches. And here, in this approach, the systematic and random effects are treated in the same way, and this approach operates in the short term, meaning all these things that cause bias within they need to be evaluated in some way. And this is not always very easy. You cannot get these components from just repeating your measurement. So repeatability oftentimes is not enough. Like it was with the titrant concentration example, however many times you do the titration, but if you use all the time the same titrant with concentration slightly different from what you think it is, then all your results will be biased. And just by increasing the number of measurements, you will not get anything better. And you cannot really evaluate the uncertainty of titrant concentration from repeatability data. So that modeling typically works in the, let's say, short-term domain. And here are the advantages and limitations of the modeling approach. Certainly, an important advantage is that it's an investigative approach. You get uncertainty budget, and also you get the uncertainty components and the sensitive factors, so you get contributions of uncertainty sources, meaning you can learn where exactly the uncertainty comes from. And this can be very helpful for improving measurement method. And obviously, it's quite good also for the education point of view. So it's an educative method. Oftentimes, knowing these contributions and having the help for improving the method is just as important as getting the uncertainty estimate. And also, it's more or less mathematically correct, but I've put this in parentheses because it's slightly more complex issue than we can discuss here. But now it also has quite important limitations. In order to use it successfully, all important uncertainty sources must be identified and quantified. And this latter thing can be quite difficult sometimes. For example, suppose you have something like contamination, sample carryover, partial decomposition of the analyte. Very, very important effects. Not so easy to investigate and quantify. And those effects may lead to the necessity of doing quite some extra work, quite some extra experiments. So doing it correctly might be quite work intensive. And nevertheless, sadly, there remains the danger to underestimate uncertainty if modeling is not done in an educated and correct way. Okay, now we go to the next one, which is the, let's say, the main topic of this workshop. This is the approach based on in-house validation data. Here, as I said already, although model is needed for calculating your result, but the uncertainty evaluation does not really need it. And what is done here is the following. All the effects contributing to the uncertainty are broken down into two pieces, random effects and systematic effects, which are quantified in these big batches. Essentially, you have one batch of random effects, the other batch of systematic effects. And so that the overall calculation of the combined standard uncertainty looks something like this, whereby this here, this uncertainty component takes care of the random effects, and this one for the systematic effects, or as sometimes we could say, for possible bias or for the possibility that recovery is below 1, or that occasionally it also for some reasons might be above 1. So that these are the components that are quantified here. And if I go to the notations that are used in the upcoming Eurachem guide, this would look like this. I'm not going in detail now what exactly is meant here, because this will be explained today and tomorrow by other speakers. Let me just show that this first one again takes care of the random effects. The second one takes care of the systematic effects. And the way the equation is presented here is that both these uncertainty components here are presented as relative components, meaning the respective standard deviation or the respective standard uncertainty estimate divided by the value of the measured quantity. And the value of the measured quantity is Q, and for getting the uncertainty finally in the units that you measure your quantity, you have to multiply this relative expression with Q. But let me perhaps not go more deeply into this, so that other speakers will later on explain this. What are here the important aspects? Here, uncertainties are quantified in large batches. So I mentioned previously that you might have things such as decomposition, sample carryover, maybe some adsorption phenomenon, etc. You don't really need to investigate those individually. You can quantify the uncertainties that come from those things as big batches, so that individual input quantity uncertainties or very detailed evaluation of all the uncertainty sources is not needed here. Secondly, importantly, this uncertainty evaluation oftentimes goes like this, that from the particular day where you did your particular measurement, you do not really use any data at all. So that you use data from the previous experiments, from control charts, from measurements with certified reference materials, which all might have been done on some different days. Meaning, the uncertainty that you get is not directly the uncertainty of your result that you obtained today, but it's rather an average uncertainty of your method that you get. And this average uncertainty, you simply apply to your result of that particular day. And finally, as many as possible of those short-term systematic effects are typically quantified as long-term random effects, so that this approach operates in that long-term domain. So that if we again take this scheme, we try to leave as few uncertainty sources into this block, because this one is more difficult and more tricky to quantify. And we want to have as many as possible uncertainty sources sitting in this block, because this can be quantified fairly easily as intermediate precision or within lab, long-term within lab standard deviation, just using some kind of reference sample, which again will be explained later in this webinar. So that you need to do less investigation and you can use a lot of the data that you already have in your laboratory. And what are here now the advantages and limitations? So first of all, you can use a lot of data that you need to acquire anyhow. So if you run a laboratory, you most probably have to run control charts anyhow, so you can use the control chart data. You have to run CRM measurements, also interlab comparisons, all those data you can use. And also, good advantage here is that you get fairly realistic uncertainty estimates, and the danger to underestimate uncertainty here is lower than with modeling. And you need less education for carrying out this approach. But of course, wherever there are advantages, there are also limitations. Yeah, and one limitation, of course, is that there's less insight. You don't learn so much about your measurement method. You don't get maybe such good information how you could improve your measurement. Also, the value in education is lower. Then also, depending on especially how you evaluate the recovery component or the systematic effect component, you might in fact obtain a quite overestimated answer. And then mathematically also it could be argued that it's perhaps somewhat less rigorous than the modeling approach. But again, this is a more complex issue. Yeah. Finally, let me comment a little bit on the interlaboratory approaches. Here, what is done is the following. Essentially, it is assumed that the combined standard uncertainty is equal to the standard deviation between laboratories. And there were two approaches, if you remember. One of them was such that all the labs used exactly the same method. The other one was that every lab was allowed to use whichever method they liked. You know, obviously, this brings in a difference. Yeah? In the first case, probably the SR is smaller than in the second case. So that the SR is the between lab reproducibility, and this approach is of course very, very simple. Yeah, you don't really need to do any calculation. But on the other hand, of course, you need to have, or such interlaboratory comparison needs to take place, or it needs to exist. And now what is important here, and why I'm reluctant to recommend this, is that these approaches, they completely ignore the situation at your lab. You essentially get uncertainty estimate from somewhere, which does not really take into account how skillful are your people, how good are the instruments, what about sample preparation, and so on and so forth. So that I would say that it is acceptable to use these approaches, in my opinion, only with highly standardized methods. For example, something like this oftentimes take place in medical analysis, where there are fully automated analyzers and where the people essentially just put sample racks into the machine and add reagent bottles and things. In such a case, I think it's very okay. But whenever it also depends on the real situation in your real laboratory, I would be very, very cautious with this approach. So let us look at the uncertainty that is obtained by the different approaches. I already mentioned that, but here we can see some summary. With modeling, you can get the uncertainty of an individual result. Your result of this sample on this particular day. With this in-house validation data approach, you get the typical average uncertainty of your method. Average uncertainty of your method as applied to different kinds of samples. Yeah? And this, of course, again holds if your control samples for control charts, certified reference materials with which you determine recovery, etc., if those are similar to your everyday samples. If they are not, then you might not get the uncertainty that is really well applicable to your everyday sample. And finally, with interlaboratory approaches, what you get is uncertainty of method in, or average uncertainty of a method in many different laboratories. So that all in all, as you see, these uncertainties do have different meanings. Yeah? And also this is quite obvious that these uncertainties numerically might be quite different even for the same method, because they come from completely different assumptions and completely different starting points. So how do you choose which approach to use? So if you have competence, if you have time, if you have data on all important influence quantities, yeah, modeling approaches, good. Yeah. But then if you have validation quality control data, results of participation interlaboratory comparisons or certified reference material analysis, and if you don't really want to do extra work, don't do extra investigations, you simply need a fairly reliable uncertainty estimate, then this in-house validation data approach is certainly a good choice. And finally, the interlab approaches I would only dare to recommend, as I said, for highly standardized methods. This is all from me. Thank you for your attention and happy to answer questions.